All right, today we are going to finish off a section of notes we started in the previous video. So we're finishing off the power law notes by applying them to situations. So before we do so, I'm just going to remind that the point form of a line is y minus y1 equals m times x minus x1, because in many times we'll be asked to come up with equation of a tangent line. So we won't just be looking for our slope, but our actual equation. So we have this example where we want to find the point slope form of a line tangent to a curve y equals negative x squared plus 6x minus 5 when x equals 6. So essentially we want to find our tangent line at this location. Now we know our tangent line there would look something like this. However, to get our actual equation of it, we will substitute our x value of 6 into our equation to get our y value where this occurs, which we can also get from our graph, but we won't always be given our graph to get. So I'll go over getting it with our equation, and then we'll find our slope of this line, or at least equation for the slope of this line, and then we'll substitute this x value in to get the value of that slope at this location. So they've given us this x value. This is technically going to be our x1 when we're using our equation of y minus y1 equals m times x minus x1. So we already have this variable. We'll solve for this one, and then we'll calculate our slope, which is this one. Now we have y equals, that can be the same as writing f of x. So that's negative x squared plus 6x minus 5. So we want to solve for this y1. We're looking for what our y value is when x equals 6. So we want to solve for f of 6. So we've got negative of 6 squared plus 6 times 6 minus 5. That gives us f of 6 is negative 36 plus 36 minus 5. So we know f of 6 is negative 5, and we know that's our y1. So we now have two of the three variables that we want before we write our equation. And we can also see this matches what our graph shows. So next thing we're going to do is find the derivative of this function so we get our slope equation for it. So if we're looking for f prime of x, that's going to be our derivative of negative x squared plus 6x minus 5. Now that can be broken up into negative of our derivative of x squared plus 6 times our derivative of x minus our derivative of 5. Now our derivative of x squared is 2x. We apply the negative in front, so negative 2x. Our derivative of x is 1, multiplied by the value in front is 6. And our derivative of a constant is 0. So this would be our equation for the slope of this line. So we want to find our slope when our x is 6. So we're looking for f prime of 6. So that's going to be negative 2 times 6 plus 6. So that's negative 12 plus 6. So f prime of 6 is equal to negative 6. So that's telling us our slope at this location is negative 6. So now we'll rewrite our equation in this form. So we've got y minus y1 equals mx minus x1, and we'll substitute what we have in. So we've got y minus y1, which is negative 5. So y minus negative 5 would be y plus 5 equals our slope, which is negative 6, times x minus x1, which was 6. And there is our tangent line in point slope form. Okay, next example, we want to find the tangent lines to curve y equals x squared minus 6x plus 5 that pass through a point 7, comma 3. So essentially, we're given a point that's 7, comma 3, and we want to find equations of our lines that pass through that and are tangent to our original graph. So we'll have two lines, something like that. So we're probably solving for two different tangent lines. Now, one key thing to know is for each of these lines, our slope as we are touching our graph here would be the same as our slope here. Same as our slope where we're touching here would be the same as our slope here. So we know that our slope of our tangent is the same as our slope at the point that they give us. Now, we know that we're going to use our slope intercept form, or sorry, our point slope form. So that's y minus y1 equals m times x minus x1. Now we've already been given x1 and y1. So essentially we right now have y minus 3 equals m times x minus 7. So we will end up with two different equations, one for each of these, where the only difference is going to be our slope. Now we know our slope is going to equal to the derivative of our function. So if we look at our function, which was f of x, is equal to x squared minus 6x plus 5, we know f prime of x, or a derivative of it, is going to be our derivative of this entire thing. So of x squared minus 6x plus 5, which is the same as our derivative of x squared minus 6 times the derivative of x plus the derivative of 5. So we have derivative of x squared is 2x. Derivative of x is 1 times the negative 6 in front gives us negative 6. And derivative of a constant is just 0. So we know that this is our slope. So we know our slope is 2x minus 6. So what we can do is essentially combine these two functions. So that gives us y minus 3 equals our m, which is 2x minus 6, times x minus 7 we'll FOIL this out. So we've got y minus 3 equals 2x squared minus 14x minus 6x plus 42. And we can actually expand this further because we're essentially told what y is equal to. So we're going to substitute that in. So we know y is equal to x squared minus 6x plus 5. We've got this minus 3. I'll combine like terms on this side. So that gives us 2x squared minus 20x plus 42. And we'll move stuff over to one side. And essentially, because we've got down to just one variable now, we can solve at what x values we have these tangent points occurring. So I'd subtract x squared from both sides, add 6x to both sides, and then 5 minus 3 is 2, so I'd subtract 2 from both sides. So that's going to give us 0 is equal to x squared minus 14x plus 40. Now, if we factor this, what we'll find is 0 is equal to x minus 4 and x minus 10, which means the x values where we have these tangent points would be when x is 4 and when x equals 10. So we can see the 4 one here. We can, because our graph was cut off here, we couldn't really see that x equals 10 one. So what we're now going to do is figure out our slopes at those particular points. So if x equals 4, f prime of 4 would be 2 times 4 minus 6, which would be 8 minus 6 is negative 2, which means we can take this equation. So we've got y minus 3 equals negative 2 times x minus 7. So this would be one of our two equations. Oops, sorry. 2 times 4 is 8, minus 6 would be positive 2, so that's positive 2. Now, if x equals 10, then we have f prime of 10 would be 2 times 10 minus 6. So f prime of 10 would be 14. So we'd have y minus 3 equals 14 times x minus 7. So here are our two equations. Okay, next example. Which point does the function y equals x squared minus 4x minus 5 have a tangent line parallel to this line of negative 3x plus 4? So here's our x squared minus 4x minus 5, and we're wondering at what point, right, is there a line parallel to this that is tangent to this? Now we can see that we're probably only going to have one point, so it would probably be over here somewhere, and we need to figure out where that point is. Now, because definition of parallel means that they will have the same slope, so we can say for the tangent line to be parallel, we need the same slope. So we know that f prime of x must have the same slope as this function, so we know that that's equal to -3. So what we're going to do is start out with our function. So we know f of x equals x squared minus 4x minus 5. We'll take the derivative of this. So f prime of x is our derivative of x squared minus 4x minus 5. So that's the same as our derivative of x squared minus 4 times our derivative of x minus our derivative of 5. So our derivative of x squared is 2x. Our derivative of x is 1 times -4 would be -4. Derivative of a constant is 0. So this is the equation for our slope at any point along this line. Now we're told that that must equal -3. So we know that -3 is equal to 2x minus 4. I'd move the 4 to the other side. So that's going to give us 1 is equal to 2x. Divide both sides by 2. And we have 1/2 is equal to x. So this is only actually giving us our x coordinate. So we don't have a full point yet. We need to get our y coordinate. So what we want to do is find the y coordinate. We know our original function was x squared minus 4x minus 5. So we're going to substitute in 1/2. So we have 1/2 squared minus 4 times 1/2 minus 5. So 1/2 squared would be 1/4. And then we've got minus 2 minus 5. So that gives us f of 1/2 is equal to -6 3/4. So we can say the point at which the tangent line has the same slope and is parallel to this would be when x is 1/2 and y is -6 3/4. Okay, next example, we're going to find the value of b if the curve y equals x squared plus 8x plus 15 is tangent to our line y equals 4x plus b. So essentially this is our curve, and we want to figure out this b value of this tangent line. So to be tangent, we need the same slope as the line that they give us. Therefore, we know y prime or f prime of x is equal to 4. So first thing I'm going to do is write this function down here. I'll write it as f of x equals x squared plus 8x plus 15. Now we're going to take the derivative of it. So that's going to be f prime x is equal to the derivative of x squared plus 8x plus 15. So f prime x is equal to the derivative of x squared plus 8 times the derivative of x plus 15. Or sorry, plus the derivative of 15. So that's going to give us 2x plus 8 as our equation. Now we know that we have a slope of 4, so we can replace this with 4. So we have 4 is equal to 2x plus 8. I would then subtract 8 from both sides. So that gives us negative 4 is equal to 2x. At this point, I would divide both sides by 2. And we have negative 2 is our x value. So we know that the tangent at a location where x is negative 2. We are then going to find the y value of this tangent point. So to do that, we'll just put back into this original function. So if we have f of x equals x squared plus 8x plus 15, and we're substituting in negative 2, if we have f of negative 2, that would be negative 2 squared plus 8 times negative 2 plus 15. So f of negative 2 would be 4 minus 16 plus 15. So f of negative 2 is going to be 4 minus 16 plus 15, which would be 3. So therefore, we know our tangent point is negative 2 comma 3. Now we can essentially utilize that and this equation to solve for b, because we have one point along this line, which we know the tangent point was here at negative 2 comma 3. So we can substitute those in and solve for a b value. So we had y is equal to 4x plus b. Now our y value was 3 equals 4 times our x, which was negative 2, plus b. So we have 3 is equal to negative 8 plus b. So 11 is our b value. Okay, next example. We have a piecewise function. So we've got let f of x equals 2x plus b when x is equal or less than 1, and it's ax squared plus 1 when x is greater than 1. So essentially, we've got one function here that connects to another function here, and we want to find all values of a and b that make f of x differentiable everywhere. So that means it's not just continuous, but our slope as we approach 1 from the left side is equal to our slope as we approach 1 from the positive side. So like I mentioned, to be differentiable, f of x must be continuous at x equals 1 and the limit of f of x must exist at x equals 1. So first we're going to look at the continuous part. So if we're looking at our continuous part, we know that our limit of f of x as x approaches 1 from the negative side would have to be this segment here, which would be this initial part. So therefore that's equal to our limit as x approaches 1 from the negative side of 2x plus b. So because this is just a polynomial, we know we can just substitute this value in. So 2 times 1 is 2. So we've got 2 plus b. Now our limit, as we approach from the positive side, so our limit of f of x, as x approaches 1 from the positive, would be this section here. So therefore, that's equal to our limit as x goes to 1 from the positive side of ax squared plus 1. Now, also a polynomial, we can substitute in this 1. So we have a times 1 squared is a, and then we just have the plus 1. Now we can say that since these two things must be equal, for the limit to exist, that tells us 2 plus b is equal to a plus 1. Now, if I rearrange this by subtracting 1 from both sides and subtracting b from both sides, that gives us 1 equals a minus b. So we've come up with an equation from our limits that show that to make it continuous. So what we're going to do next is look at our slopes. So they also have to have the same slope at x equals 1 if they are differentiable. So we'll just quickly come up with the derivatives of both. So we had one function that was 2x plus b, another function was ax squared plus 1. So f prime x is equal to our derivative of 2x plus b which is the same as our derivative of 2x plus the derivative of b, which derivative of 2x is 2, and derivative of b, because that's a constant, would just be 0. So we know that this one had a slope of 2. For this one, we have f prime of x is our derivative of ax squared plus 1. So that's the same as our derivative of ax squared plus our derivative of 1. So derivative of x squared is 2x multiplied by that a. It's just 2x. And then derivative of, sorry, that should have been a 1. Derivative of this constant is just going to be 0. So we have this one being 2. Well, this one's 2x. Or sorry, 2 times not x. Our variable that is still in there was a. Because when we took the derivative of x squared, that gives us, oh yeah, 2ax. So I'd forgot to include that a that was in there. So what we know is f prime of x is 2 when x is equal or less than 1, and it's 2ax when x is greater than 1. Now, if we look at our limits of f prime, we know that our limit as x approaches 1 from the negative side of f prime x would be our limit as x approaches 1 from the negative side of essentially 2, which just doesn't have a variable in it, so it's just going to stay as 2. Now our limit as x goes to 1 from the positive side of f prime x is going to be our limit as x goes to 1 from a positive side of 2ax. Now if we substitute this 1 in for this x, that just becomes 2a. Now from this, because we know these must be equal for it to be differentiable, we know that 2 is equal to 2a. So therefore, if we divide both sides by 2, 1 is our a value. Now, if we go back up to this equation we had earlier, where we've got 1 equals a minus b, we can substitute this 1 in for a value. So 1 is equal to 1 minus b. Subtract 1 from both sides. So that gives us 0 is equal to b. So we have solved it. Our a must equal 1 and our b must equal 0.